Hey everyone, and welcome. Today, we are diving into something you see all the time in science, a single, neat, average result that comes from combining dozens, maybe hundreds of different studies. But here's the thing, what is that average actually hiding? Well, it's often a much messier and way more interesting story.
This quote right here really just nails the whole problem. A 40% average risk reduction sounds great, right? But think about it. One possibility is that it works reliably and consistently for everyone. Awesome. The other possibility is that the effect is completely all over the map, a massive help for some people and barely doing anything for others. The average is the same, but the reality is totally different. The average alone just doesn't cut it.
So that brings us to the big question for today. When researchers are staring at this pile of varied, sometimes conflicting results, how on earth do they figure out if they're looking at a stable, consistent effect or one that's wildly unpredictable? How do they tell the difference?
To answer that, we've got to talk about the signal and the noise. You see, in any collection of studies, the differences you observe in their findings are always a mix of two things, what's real and what's just random statistical chatter. So our first job is to pull those two apart.
Think of it like this. Every single study is trying to measure some true effect out there in the world. But, they all use slightly different groups of people under slightly different conditions. So there's always going to be some random error, just from the luck of the draw. The variation we actually see is a mashup of the real differences and that random error. The whole trick is figuring out how much of it is real.
Okay, let's make this visual. Take a look at plot A. We've got results from a bunch of studies, and you can see they're a bit scattered. But look closely at those horizontal lines, the confidence intervals. They're super wide, and they're all overlapping with each other. This paints a picture where, yeah, it's totally plausible that all these studies are actually measuring the exact same thing, and the differences we see are just that random error we talked about. It's basically noise.
Now, contrast that with plot B. The results are just as spread out, but whoa, look at those confidence intervals. They are tiny. Each one of these studies is incredibly precise. Suddenly, it's pretty much impossible that they're all measuring the same underlying effect. The variation we're seeing here isn't just noise anymore. It's a real, genuine difference across the studies. This is the signal.
And that signal, that real variation, has a technical name, heterogeneity. It's not just any old variation you see on a chart. It's the variation that's left standing after you've stripped away all the random statistical noise. It's the pure measure of how much the true effect actually differs from one situation to the next.
Okay, so how do we actually put a number on this? How do we measure it? Well, researchers have a pretty neat toolkit of stats designed specifically to hunt down and quantify this heterogeneity. Let's walk through the basic idea.
It all starts with a number called Q, which is just the total amount of variation you can see in the data. Then, you figure out how much variation you'd expect to see just from random chance alone. The difference between what you see and what you expect, well, that's the excess variation. That's your signal. And from that little bit of excess, researchers can calculate two super important numbers that tell the whole story, t squared and I squared.
First up, let's talk about t squared, or tau squared. This is an absolute measure. It tells you the actual variance, the literal spread of the true effects, in the same units as the original study. So if the study measured blood pressure, t squared is in units of blood pressure squared. It's the tangible amount of real-world difference.
Now, variance can be a little hard to wrap your head around, so to make it more intuitive, we often just take the square root of t squared, and that gives us tau, or t. This is simply the standard deviation of the true effects. It makes the spread way easier to understand, letting us say things like, okay, we'd expect most of the true effects to fall within this specific range.
The other star player here is I squared. Now, unlike t squared, this one is a relative measure. It's a percentage, and it tells you what chunk of the total variation you're seeing is due to real differences versus what's just random noise. It's basically a signal-to-noise ratio. So if you see an I squared of, say, 75%, it means 3/4 of the variation you see in the results is the real deal, and only 1/4 is noise.
And this chart makes it super clear. Just imagine all the variation in your data is one big pie. I squared is the slice of that pie that represents true, real, meaningful variation. The rest of it, that's just the random sampling error. It's as simple as that.
All right, now we get to what is probably the most important part of this whole explainer, and it's the thing that trips people up all the time. It's the crucial difference between the amount of variation, t squared, and the proportion of variation, I squared. They seem similar, but they tell you two profoundly different things. Check this out. Here we have two scenarios.
In both cases, the I-squared is exactly the same. About 58% of the variation is real, so the proportion is identical. But now look at the t-squared values. In scenario A, the amount of real variation is teeny tiny. The true effects are all huddled closely together. But in scenario B, the amount of variation is way bigger. The true effects are really spread out. Same proportion, but a completely different real-world story.
Okay, now let's flip it. In this case, both scenarios have the exact same t-squared. This means the amount of real-world spread is identical between them. But look at the I-squared. In scenario A, which probably has very precise studies with little random error, that spread makes up a huge chunk of the total variation, a high I-squared. But in scenario B, maybe the studies were less precise and there's just way more random noise, so that same amount of real spread gets drowned out by all the noise, resulting in a much lower I-squared.
So, we've learned how to measure the amount of real variation and the proportion of real variation. But so what? What's the point? Well, the point is to make much better predictions about what we can actually expect to happen in the real world.
And this brings us to this critical distinction, the confidence interval versus the prediction interval. Now, you've probably seen confidence intervals all the time. They're all about the average. They answer the question, how precisely do we know the mean effect? But the prediction interval is different. It uses our measure of heterogeneity, that t-squared value, to answer a much more practical question. What's the likely range of true effects we'd see in one new future situation? It's about the real-world spread, not just the average.
To really see why this matters so much, let's just do a quick thought experiment. Let's imagine what happens to these two different intervals as we just keep adding more and more and more data.
So let's start with just a handful of studies, say 6. At this point, everything's a little bit blurry, right? Our confidence interval for the average is pretty wide because, frankly, we're not very sure what the true average is. And the prediction interval is even wider because it has to account for our uncertainty about the average plus all that underlying real-world variation.
Okay, but what if we keep going? What if we don't just have 6 studies, but instead we manage to find 1,002 of them? And here it is, the big aha moment. With over 1,000 studies, our confidence interval for the average shrinks down to basically a single point. We know the mean effect with almost perfect precision. But look at the prediction interval. It's still wide. Why? Because collecting more data doesn't magically make real-world differences go away. All that data just makes you more and more certain about exactly how much real variation there truly is.
And that right there is the single most important takeaway from all of this. Knowing the average with perfect certainty is fantastic, but it doesn't change the fundamental fact that the effect varies in the real world. That heterogeneity, that real-world spread, is an essential feature of what you're studying. It doesn't disappear just because you collect more data.
So the next time you read a headline or see a report that boasts about an average effect found across many studies, you'll know to ask a much smarter question. You won't just ask, what's the average? You'll ask the far more important question, okay, but how much does it vary? Thanks for joining me.